less than 10 seconds.
Hey everyone, Michael Unger here from the HR MacMillan Space Center, here with our bonus interview for our event, Cosmic Nights Dark Matter. Now, of course, as you have seen already in our event, thinking about dark matter, we're thinking about the universe in very different ways. And so I thought for this bonus interview, we would talk with someone who also thinks about the universe in a very different way, in something called the holographic principle. So Dr. Marcel Franz is a professor of theoretical physics at the University of British Columbia, specializing in interacting and topographical states of quantum matter. He's also the deputy director of the Stuart Blusson Quantum Matter Institute. Hi, Dr. Franz, how are you?
I'm good. How are you?
I'm great. So maybe to start us off here, tell us a little bit about yourself, your research, and what you do at the Quantum Matter Institute. Because, you know, when I hear that title, Quantum Matter Institute, it kind of like gives me some chills, because it brings me personally back to my comic book days and Reed Richards, Mr. Fantastic from the Fantastic Four, opening up portals into different dimensions. I see that this may not actually be a reference that you would know because you grew up in old Czechoslovakia, but maybe there is some references to draw upon to tell us about like yourself and your research.
So I'm a quantum physicist working on properties of quantum particles like electrons and protons and solid state physics. And indeed, I was inspired to do some work on things like black holes and wormholes from my readings of science fiction literature. I was an avid reader since my young age, reading everything from Heinlein, Arthur C. Clarke, Asimov, all the way to more modern authors of today. And of course, the premise is that humans travel between the stars, even to different galaxies, and it doesn't take them hundreds or thousands or millions of years, but they do that almost instantly. So there you have a wormhole concept.
So could you tell us a little bit about what we're talking about when we say the holographic principle and what that actually means?
So holographic principle means what it sounds like. It basically postulates that the world, in some sense, is a hologram. So in our three-dimensional space, everything that happens in our three-dimensional space between you and me and so on is somehow encoded on a boundary of this three-dimensional space, which is only two-dimensional. Just imagine a bulk sphere and it has a two-dimensional surface. So everything that happens here in this room or your room is somehow encoded on a distant boundary. And it doesn't look like, you know, this is a valid principle because we feel our world to be three-dimensional. But when you dive down to quantum physics of black holes, for instance, then it seems like that's the only interpretation that makes sense at that level of thinking.
So how exactly do black holes relate to this? Because I know that you've done some work with something really interesting. You have taken an ordinary pencil and using the analogy of that in how we can study black holes.
So black holes are, of course, these enigmatic objects that exist in our universe. They are the densest form of matter that you can find anywhere. Their mass and density is just so large that nothing, not even light, can escape. And some very interesting things happen when you start thinking about black holes from the point of view of quantum physics. And this is famous work that people like Stephen Hawking did some 20, 30 years ago. And it is that work that precisely leads to this holographic principle through pointing out certain paradoxes that occur. If you just treat black hole as an ordinary three-dimensional object and you think about it from the point of view of quantum theory, then you end up with some unreconcilable paradoxes. And these can be reconciled by postulating this holographic principle, which you mentioned in just
Yeah, so you do something called a graphene experiment, and that's kind of like where I was talking about where this pencil comes in. So can you maybe tell us about what the graphene experiment is and how it actually works?
Okay, that's a very good question. So, black holes exist, and we now have a sort of irrefutable evidence that they exist as astrophysical objects. Nobel Prizes were just given for, black hole work that showed the evidence. Now, the problem with investigating black holes is that we can look at them from very far away, right? The nearest one exists at the center of our galaxy, which is very far away in terms of human distances. So we can observe them, but we cannot really make any experiment, right? We just see the light that comes from the vicinity of the black hole, and that's it. That's what we can observe, and that's what we can try to understand. However, if we want to make some experiments that reveal more about the black hole than we can watch from 70,000 light years away, there's actually other ways, and this is where this graphene works comes in. This is not really my invention. Other theoretical physicists noticed that there exist quantum systems that you can actually investigate in a lab, which in some very precise ways behave as black holes. So they don't suck you in as a black hole would, or they don't do certain things that you would normally associate with black holes. On the other hand, they have some other properties that are really in one-to-one correspondence between with what a black hole would do. And so this is where this graphene experiment that we proposed would come in.
Yeah. So maybe take us through physically, because it's hard for me to picture, my mind when I first started reading about this. Like, this seems wild. And when I think about what you do at the Quantum Matter Institute, I guess this does qualify as some of the work that you do. So maybe step us through exactly how this experiment works.
Okay. So let me first tell you about one interesting property of the black hole, which is maybe not very well known compared to some of the other ones. So black hole is so-called maximally chaotic. What this means is that you start from a black hole in its normal state, and you perturb it in any way by, say, throwing a particle in it or trying to manipulate it in any which way. It turns out it will go back into its natural state in the shortest possible time that is consistent with our understanding of the universe. So nothing can go from this disturbed state to its natural state any faster than the black hole. And this is what it means for a system to be maximally chaotic. Now, this has been thought of initially as a unique property of a black hole. Nothing else can equilibrate or thermalize as fast as a black hole can. However, in recent 10 or so years, people have discovered quantum systems that can be grown in a laboratory, which have the same property. They're maximally chaotic, and they share this and some other properties with black hole. And this opens a possibility that you can actually fabricate a system that you have in your lab. You can investigate this property, and you are essentially probing something that only a black hole has, other than your system in the lab. So you don't have to travel 70,000 light years to the center of our galaxy to do this experiment on a black hole, which would be extremely difficult, impossible really. But you can actually do this on a desktop, on the tabletop, in a laboratory. So that's the experiment that we proposed. It was not really clear what concrete systems that you can fabricate in a laboratory have that property. So we have proposed one that is kind of perhaps most easily amenable to analysis, and this is precisely a graphene flake, which is basically a piece of very, very tiny sliver of material that exists in your ordinary pencil.
That's amazing. When I think about things that are surprising about science, trying to connect these ideas of a pencil and a black hole and how you may actually use that as an experiment, just fills me with joy and wonder. And And I'm curious for you yourself, has there been anything that has surprised you along the way and maybe brought up more questions going through this process and doing this experiment?
Oh, definitely. So at every level, there's always more questions than there's answers. So we do one calculation, we predict something, then we go to our experimental colleagues, we suggest an experiment to them, and they measure and they find something usually different from what we predicted. So it's this constant dialogue between what we understand as theorists and what our experimental colleagues measure. And the greatest joy perhaps that someone like me, quantum theorist, can experience is when you do a calculation with your pen and pencil or on your computer, and then your colleagues in the lab actually measure something that is in agreement with that calculation. And that unfortunately doesn't happen as often as we would like, but when it happens, then we can say we really understood something, and that's a very satisfying feeling indeed.
Yeah, I'm trying to imagine sort of like that cliche of the scientist in the lab and having that eureka moment. And now I'm sort of picturing now perhaps you working on some calculations and maybe just sort of taking a pause to moment and just staring at your pencil and thinking about the graphene in that pencil and thinking about that pencil now as it relates to black holes. Because of course, that cliche of the eureka moment doesn't actually really happen in the lab, does it?
Those moments actually happen, but for me at least, they usually don't happen in my office. So in my office, I sit, I do these calculations, and the standard situation is that you do calculations and something is not working, something is not quite right, and you don't know what it is, and you try something else. And then often eureka moments happen in unexpected places. On a weekend, I go for a hike, and as I'm climbing up the hill, suddenly that little thing that was bothering me clicks. And now I know. And then sometimes I have this urge to turn back from my hike and run back to my office and finish the calculation, or I'm kind of unhappy that I cannot do it in my head while out there. Or sometimes this may happen, at 4 a.m. in the morning when I just wake up and then I can't sleep anymore. So these insights happen at random times, and actually rarely happen in, when you would expect them to happen, when you're actually sitting in your office and doing calculations. Usually, then nothing happens.
Yeah, no, I think that's great inspiration, because I think like for anyone going through moments of conflict, trying to figure out something that they don't have a solution for, sometimes the best thing to do is just to stop what you're doing and like what you do, go for a hike and go outside, and all of a sudden the solution may just come to you when you're not thinking of it.
That's exactly right. Now I have to also say that, of course, sitting in your office and doing these calculations is necessary, right? Without those, you will not have any eureka moment, because then there's no really a well-defined problem or issue that kind of sits in your mind that you can easily resolve, right? So both parts are necessary, but I always encourage my students, when they're stuck with a problem, just go out there, do something else, go for a run or whatever you like to do, and that usually helps to flip this switch in your head. You look at the problem from a different direction, or you suddenly think about it differently, and then hopefully the log jam is broken and the idea crystallizes.
Wonderful. So one final question I just want to leave you with, Dr. Franz, is, you're a theoretical physicist. You're thinking about the universe in this different way, perhaps just like Reed Richards did. And he sort of like took that extra step and found this portal into a different dimension. Now, I know that's not exactly what you're doing, and that's not exactly what theoretical physicists do. So for you personally, what draws you to this work? Like, what really gets you excited to solve, some of these deep mysteries? Like, you're not, trying to find a pathway into a different dimension, but you're maybe meeting Reed Richards somewhere halfway. So for you personally, what really draws you and gets you excited about this work?
Well, partly it is to what I just mentioned, to discover how things in nature work, where when there's some experimental findings, we don't understand them based on existing theories. If we can push this understanding and what our colleagues find in the lab closer together, that's immensely satisfying. But also this distant dream that, one day humanity will travel to stars, and how do we do that? The constraints of current physics as we understand it are really daunting. To send a human expedition to the nearest solar system, I mean, that's a hugely difficult, impossible endeavor at present. So we have to work on this. We have to discover other ways of doing that. And I tell you one example. So wormholes, right? The standard trope of science fiction literature. According to Einstein theory of relativity, classical theory of relativity, wormholes, sort of cannot really exist as stable objects. So unfortunately, to the extent that we believe Einstein, wormholes are a non-starter. Now, 3 years ago, some famous physicists from Princeton actually showed that this is true only within the framework of classical theory of relativity. If you add quantum effects, you can actually stabilize wormholes by a serious, solid calculation. So, this is a theory at the edge of current research, but it shows the possibility, at least, that something that we thought was completely prohibited until that point is possible under some circumstances. Now, still immensely far from actual realization of such a wormhole, but at least we know that it's not completely impossible. And moments like those are really fantastic because they expand the spectrum of possibilities for the whole humanity, right?
Yeah, wonderful. Wow. Thank you so much, Dr. Franz, for taking time out of your day. And hopefully we'll run into you again somewhere in the universe.
Yes, thank you very much. It was a pleasure.
Take care.